All right, hello, Senior Recovery Earth Science. I am your teacher, John McNerney, and I took this PowerPoint from one of my colleagues, so don't get mad at me if you don't like it. I will be making my own for the next units, but I was in a little bit of a time crunch, so this PowerPoint's great, don't worry. Okay, so we're going to talk about the origin and the evolution of the universe. So the origin of the universe is a highly debated topic, but our best explanation for it is the Big Bang Theory. Like it says there, it's only one possible explanation, but it's the one that has the most evidence attributed to it by scientists and all sorts of physicists. So all matter and energy in the universe was once compressed in a very small and extremely hot and very, very dense singularity. So what we're talking about is something smaller than the tip of a ballpoint pen, and something with all of the mass in the known universe. So if you think about that, it's kind of strange to think about, but we'll try and talk you through it a little bit here. So what happened was that very small singularity, very hot, very dense, something happened to make it expand rapidly. And so when that happened, a bunch of matter and a bunch of energy emanated from that singularity, and that small little teeny ballpoint pen singularity turned into our known universe. So when that happened, space and time was created, and that just has to do with physics and light and matter and all sorts of higher level things that are going to take too long to explain. So what we need to know is the Big Bang Theory was essentially everything in the known universe was a small, very dense, hot singularity that rapidly expanded, like faster than you can blink your eye type of deal. And it is still expanding today, and I'll tell you why. So we have this thing called the Doppler effect, and essentially what's going on is we have light and sound interacting with each other, and they interact pretty similarly in their energy forms. So the Doppler effect is going to cause a shift in the frequency of light waves as the source and or observer moves. So if you think about like a police car or an ambulance, this is the example that everyone gives. When it's going towards you, the frequency starts to pick up and it starts to get higher pitched. So that example is this right here. It's called a blue shift. And so that's when the light source and the observer are moving closer together. So right here, for both of these observers here, the frequency and the pitch is the same because they're the exact same distance away and this source is not moving. For these observers, it's much different. So the source here is moving towards this observer and creating a higher pitched, higher frequency wavelength. So they're experiencing it differently than this observer here, who is experiencing it as it's going away. The frequency gets longer and the pitch gets longer. So when that police car is coming towards you, it's kind of scary because it's coming at you and the pitch is increasing and the frequency is increasing, but as that police car is moving away from you, as we see here in this red shift, the frequency and the pitch are decreasing. So it sounds like it's getting farther away because it is, and that's just what the light or the sound energy is doing. So I guess the important thing to know is that the red shift is when the light source and the observer are moving further apart. So right here, this is the source, and the observer is moving farther apart. The spectrum of observed light is longer, and the frequency is longer. Whereas if the source is moving towards an observer, the frequency and the pitch are increasing. And I say pitch because I want you to think about that example of the police car or the ambulance siren. So that's redshift and blue shift and the Doppler effect. All right, so this is light. And so you know how it kind of is similar to sound. So when we get a redshift here, what's going on is all of these colors have different frequencies and different wavelengths. So when we see a redshift, we know what frequency and what wavelength is being transmitted to us. So we can kind of get an estimation that what we're observing is moving away from us. So a prediction that we have from the Big Bang Theory is that the universe is still expanding. And we have two guys, Vesto Slipher and Silver and Edwin Hubble. They both took measurements of light and wavelengths, and were able to kind of extrapolate that due to the red shifts that they were receiving through their telescopes and monitoring devices, that galaxies were actually moving away from us. So most galaxies are moving away from the Earth, and the universe is still expanding because we see this red shift left over from the Big Bang. So here we have cosmic microwave background radiation. So cosmic background microwaves, I don't know where to put my face, are essentially space is supposed to be absolute zero because there's nothing in it, right? Well, that's not what we observe. What we observe is this small energy here, 2.3 or 73 Kelvin, and it's in the form of cosmic microwaves. And so we think that that is the leftover radiation that has redshifted into the microwave region, which is just going to be over here in this area. So we know the frequency of the wavelengths, and we know where that in turn correlates to like shifting, so redshift or blue shift. And so since we know that it's a redshift in these outer reaches of, well, not the outer reaches, sorry, the parts of space that are empty, then we can kind of make a conclusion that the observed temperature of the cosmic microwave background radiation is there because of leftover radiation from the Big Bang. So essentially what we're thinking is that this energy that we see in here that we do not know where it came from the Big Bang, and the universe is still expanding because we still see evidence of redshift and microwaves. Okay, so quickly, this is the Hertzsprung-Russell diagram, and essentially what it's saying is with higher luminosity, that's like the brightness of a star, you're going to get a lot of the times higher temperature. It doesn't always correlate like with the supergiants. They're just always very bright. They have a very high luminosity. But you're going to get things like the main sequence here when fusion is occurring. You're going to get these red giants or red stars. They're going to burn less hot, and they're going to have a decreased output of luminosity. So the less hot it is, the less bright the star is. So you're going to get these white dwarfs over here. They don't really follow the main sequence all that well either because they're very hot, but they don't have a lot of luminosity. But for the most part, the hotter you get, the more luminous something is. So that's just something to think about. Okay, so we're going to get to the star cycle here, and this is a pretty interesting thing. I'm just going to put it over here, right here. So we'll go over this. All stars, regardless of their mass, start the same way. Hydrogen and other gases, normally helium, condense to form a nebula. So a nebula is just a bunch of cosmic gases and matter kind of spinning around in the middle of space. And as more matter and friction occurs when they're spinning, there's going to be more heat in the system, and with more matter, there's going to be more gravity. So this thing starts to kind of condense and create a very small, hot singularity, like we remember from the Big Bang. And so when it creates that small, hot singularity, then the center of the nebula will continue to collapse and spin. It will form a protostar, and that's due to nuclear fusion. So once fusion occurs, then we're going to start getting star formation. So you can have low mass stars and high mass stars. Our sun is a low mass star. So we'll look at this. It's a big mixture of hydrogen and helium, which are very low mass gases. So what happens is you get the formation of the star, which is what we have now. So we're in a relatively young galaxy. And then eventually that burns all of its fuel and it expands and becomes a red giant. That red giant will expand and it will burn up all of the planets in its path. So Earth isn't going to do so hot once it turns into a red giant, or it will be hot. And then it will turn all those planets into gases, form a planetary nebula, and then that nebula will either condense and become a white dwarf, or it will go back into the star-forming nebula part of its life cycle, and then go over this whole 4 steps again. And then on the other side, if we have a high mass star, you're going to see a lot of like iron in there, or it could just be a huge star full of hydrogen and helium. But we're talking about high mass stars here. And so with a high mass star, it's going to eventually burn up all its fuel. It will expand, turn into a red supergiant. Once that red supergiant burns up all its fuel, it will turn into a supernova. And then from that supernova, there's a variety of things that come into play here that we won't get into. It can either turn into a black hole, and that's an extremely dense area, or it can turn into a neutron star, which normally these eventually explode, or it can go back into a star-forming nebula and start that process all over again. So that's important to know, the star cycle. Okay, and so distances in the universe. It's not important that you really know these, just know that these are distances. The astronomical unit is the distance from the Earth to the Sun. That changes all the time because the Earth wobbles on its tilt, and so it moves a little bit on its rotation all the time. So, and a light year is the distance that light travels in 1 year. And so we'll talk about parallax because that's something that we need to talk about. So essentially, the Earth spins around the Sun. And what we do is we look at stars. And so when we're observing stars in the night sky, and as the Earth spins from season to season, we see the stars move. So when stars are very distant, we don't see them move all that much. And that's just because they're so far away that our observable realm doesn't really take that into effect, the movement, because they're so far away, what we're looking at doesn't change all that much. But these closer stars, like the zodiac constellations, we see them change by season to season. And so that's what we're going to think about with parallax, is the distance between the Earth and observable universe, and how that changes with its revolution around the sun. So, that's why you get different seasons and different constellations in different seasons, is because of parallax. And so constellations are just a group of stars in the night sky. Right here we've got the zodiac constellation. What's important to realize is that due to parallax and the changing revolution of the sun, of the Earth to the sun, we see changes in constellations that are close and observable. So you may be a Sagittarius now, but in 20,000 years, you could be a Capricorn. So that has to do with parallax too. So it's just important to know that astrology is very cool, but it's ever changing, and it doesn't have much of a basis in science. Okay, so if you have any questions, go ahead and ask me. Make sure that you are looking over the PowerPoint before you take the quiz, because I kind of go over these quickly, and you should be extrapolating your own evidence for answers through the PowerPoints and through my lecture. Okay, so have a good one.